we'll finish the remaining 2 questions. This tutorial is about basic citation and vibration isolation. We'll send the code for everybody. Okay, so we solved up to question number 5. And okay, we started the question 6, but not finished. An electric motor of mass 68 kg is mounted on an isolator block of mass 1200 kg, and the nature frequency of the total assembly is 160 CPM with a damping ratio or factor of zeta equal to 0.1. See the figure below. So we have the isolator block is 1200. This is the isolator. And the motor is 68 kg, but they are rigidly fixed, become one mass. And stiffness is the, this part is maybe rubber pad or soil that will give stiffness and damping. So it is given that omega n or Fn equal to 160 CPM. This is the initial frequency after this assembly. If there is an imbalance in the motor that results in a harmonic force of F equal to 100 sine 31.40, determine the amplitude of vibration of the block and the force transmitted to the floor. Okay, so we need to find, we take the imbalance is given as a harmonic force. So this is F naught, and this is omega. And from Fn, we can find omega n equal to 2 pi over, Fn over 60. So this is given as RPM. We need to divide by 60. Okay, if n is not in hertz, this is CPM, cycle per minute. So we can get the amplitude x equal to F naught over k, and we can get R, of course, omega over omega n. Okay, we need to multiply this by, okay, so we already did the conversion of this, divided by 60, divided by the square root of 1 minus R squared whole square plus 2 zeta R squared. Okay, this will give us the amplitude of the whole assembly, which is the motor and the block. The force transmitted is F equal to Ft equal to Kx square root of 1 plus 2 zeta R squared, because we have spring and damper. Okay, question number 7. A sensitive instrument with mass 113 kg is to be installed at a location where the acceleration is 15.24 centimeter per second square at a frequency of 20 Hz. It is proposed to mount the instrument on a rubber pad with the following properties: K equal to 2802 Newton per centimeter and zeta 0.1. What acceleration is transmitted to the instrument, and what force is transmitted? Okay, we have acceleration. We have the base is moving with acceleration with omega square y equal to 15.24 centimeter per second square. Okay, the transmissibility we have is equal to square root of 1 plus 2 zeta R square divided by 1 minus R square all square plus 2 zeta R square equal to x over y, right? So if you multiply by omega square here and divide by omega squared, then we are not changing the equation, but you are changing the terms. that instead of x over y becomes acceleration divided by acceleration. Y omega square, we know it is 15.24, and then we can find omega square x, which is the required acceleration. Okay, because the question is to find the acceleration transmitted, which is omega square x. Okay, and then we can find the transmitted force. Okay, we have K and we have zeta. Okay, and we have the frequency is omega, so we can find omega n, then the transmitted force becomes okay, 3.6 Newton, that's the answer. It's also equal to if not over over ft, sorry, ft over f naught. Okay, and the transmitted force in the basic citation, I think we talked about this before, it can be written as minus k z minus c z dot, okay, which is also equal to m omega square x, if you want the magnitude, okay. This is equal to m x double dot, and if t also equal to the summation of the vector sum of the spring force and the damper force, which is kz minus c minus kz minus cz dot. So the magnitude of ft becomes m omega square x. Okay, I think you can find this in either in this tutorial. Yeah, it is here. So that you can alternatively find the transmitted force as Ft. This is for n-dam system, but it's the same thing for the dam. That the transmitted force equal to mx double dot. Okay, so it is m omega square x that will give us the amplitude or the magnitude of the transmitted force. Okay, Ft is also sinusoidal, but you want the peak value. واضح? Okay. Okay, this will be lecture number 10. Okay, this is the last section in this chapter, which is about an important part in vibration, which is very, it's widely used in the practice. You can use those are the vibration measuring instruments that can be used to measure the vibration. The purpose of measuring vibration is monitoring the machines with time to see how the status of the machine, they call it diagnosis of machines, in order to see whether it is working healthy or safely or not. The idea is based on what we did so far, which is you build up a spring mass damper system inside a casing, a rigid casing, so that the vibration point or the point at which you want to measure the vibration, you place the casing. The casing, as you can see here, is rigid. So this will take the vibration of the base and will give excitation to the spring mass damper system inside the casing. Okay, this is the rigid case. So you can see this is base excitation. But the system we have is made so that you can make measurements. Okay, what you need from this unit, it's called seismic unit because it is measuring the vibration of the ground or the foundation. Okay, the base. It is measuring the vibration of the base. So ultimately, what you want is to find y, which is this is the unknown part. Inside the system or inside the casing, the mass will vibrate with x. So x and y are the absolute quantities. There is a difficulty in measuring x because that is inside the casing, which is closed. And if you want to measure the vibration of the mass inside, you can put another sensor or another device. For example, you can put a potentiometer. Potentiometer is depends on the change of the value of the resistor. Okay, so you have a coil or a resistor, and then you have a pointer. Okay, this pointer is moving up and down, and accordingly it is changing the value of R. And then if this is part of a circuit, electric circuit, it's going to change the voltage. And then you can have a relationship between the displacement and the voltage. But this is not X, this is Z. Inside the casing, you are taking the difference in displacement. So unless that the potentiometer is taken outside the casing on the surface, okay, or not on the surface, on the ground, which is not possible. So what quantity you will get from the seismic unit is Z, not X. So you can base your equations or find your equation based on Z rather than X, because inside you can put, as I said, circuit or another sensor that can measure the relative based on the relative displacement. Okay, so we will find an equation that is relating Z and Y. Okay, this is based on what we did before in the previous section about base excitation. And the equation is the same, that mx double dot, comes from the sum of forces, equal to mx double dot equal to minus c x dot minus y dot minus k x minus y. We have x is the displacement of the seismic mass, which is this inside the casing, inside the unit, m, and this is absolute quantity measured from fixed reference. Y is the displacement of the vibrating body, and this is required. Okay, this is what we want. And the relative displacement is given by z minus equal to x minus y. Okay, and we will do that. We'll assume that y equal to sinusoidal as well, which is y sin omega t, to be in the scope of the course. Okay, then substituting z in, as x minus y inside the equation of motion, we will get m z double dot plus c z dot plus kz equal to m omega square y sin omega t, which is the same equation we derived in the section of base excitation. And we say this is identical to the rotating imbalance. And here we have, instead of x, we have z. Okay, and the forcing term is omega square y instead of me omega square. Okay, the steady state solution is the important part, of course, because the total solution will not give you y. The total solution will have the transient solution. The transient solution will give x, depends on the initial conditions. Okay, so what you want is the steady state solution. So when you use a sensor to measure vibration, you have to start recording after few times, like few seconds, and so that the steady state will be the result. Okay, you don't start recording immediately. Okay, this will give you irregularities. Okay, that is related to the, even if it is 0, initial conditions, still we will have the transient solution will be part of the total solution. And with damping, the transient solution will die out, will decrease to 0. Okay, so the important part of the seismic unit is the steady state. The steady state solution, we also derived it last time. It is Z equal to M omega square Y divided by the square root of K minus M omega square all square plus C omega square. And we can put this in dimensionless form. We divide by K, multiply by K, we will get Y omega over omega n square divided by square root of 1 minus omega over omega n square all square plus 2 zeta omega over omega n squared, right? So we also find Z before, which is the same equation here, and we used it for the transmitted force for base excitation. We said that Kz is the transmitted force for undamped system, and if you multiply by square root of 1 minus 1 plus 2 zeta omega over omega n squared will give you the transmitted force for damped system. So this is not a new equation, is already we derived it before. Okay, now but the uses of Z now is different. We are using this equation to make measurements. Yeah, we want to find Y, but there are two equations or two unknowns. Okay, can you identify the two unknowns? ما عند اللي حسن وأحمد. Yeah. Y is the first one. Yes. Omega is unknown. Okay, this is at the vibrating body is, you can think of this as the table, and this table is vibrating. So you need to put the seismic unit on the table to measure the vibration of the table, or you imagine that you are putting the sensor or the seismic unit on a vibrating machine. Let's say the AC unit. Okay, the AC unit, you put the sensor on the top, on the casing, right? You don't put the sensor or the seismic unit inside the machine. So it is always used to measure the surface vibration. Okay, whether this is a pipe, part of a machine which is vibrating, then you put the sensor on the pipe, which means on the surface. So it is measuring surface vibration. And there are two unknowns here, Y and the frequency of excitation, omega. So in the equation we have of Z, we have Y is unknown and omega over omega n is unknown. We know omega n, but omega over omega n, because omega is unknown, becomes omega over omega n is unknown. So we have two unknowns. We have only one equation with two unknowns. And that's make it, we have to find a solution for this. We cannot use this equation for all values of omega over omega. Okay, it will be, it is a linear equation, first of all, that Z, you can put 0 over Y on one side. Okay, let's say we will find 0 over Y. Okay, and the equation is then linear. So we don't know how much is omega. Zeta is known because this is part of the seismic unit. Omega n and zeta are known, but omega and Y are unknown. Okay, also there is the phase equation. It's important for the phase. If you are measuring a sinusoidal wave, like as mentioned here, that Y equal to Y sin omega t, then the phase is no problem. But when you have the base is vibrating with two frequencies, which means Y1 sin omega t plus Y2 sin omega 2t, then the phase is very important here. Okay, the phase depends on zeta and on omega over omega n. So you will see that not all values of zeta will be suitable here. Zeta equal to 0 is one of the possible cases. And the other one is zeta equal to 0.7 because there will be straight line between the phase and omega over omega n is a straight line equation, which means almost straight line. So you can approximate it as a straight line. And then you will have only shift in the amplitude. Okay, and that will be a good choice. Either zeta equal to 0 or zeta equal to 0.7. Otherwise, if you choose another zeta, it will have nonlinearity in phase as well. And then adding terms, you will use the principle of superposition. Okay, anyhow, I will focus on the amplitude, not on the phase. Okay, but it's zeta equal to 0, zeta 0.7 are the most suitable ones. Okay, for the amplitude, here it is shown amplitude ratio, z over y. This is very important, the graph, although we don't use it to calculate quantities, but we can use it to identify the ranges of omega over omega n at which the this seismic unit is useful. Okay, so z over y. Okay, you can see for omega over omega n, there are two shaded areas here. This is the graph of z over y versus omega over omega n for different values of zeta. Okay, as you can see, zeta equal to 0 is shown, zeta 0.25 is shown, 0.5, 0.7, and 1. Okay, for the range when omega over omega n is very much greater than 1, all the curves becomes equal to unity. Okay, here the shaded area is shown from 2.5 to 5. Okay, let's say from 3 to 5. And you can see that the curves are almost merging at 1. But imagine this is higher. Let's say this is 10 or 20. Then the effect of zeta is negligible, right? So zeta equal to 0, zeta equal to 1 become one curve in this range. But what is the important part in this range is that how much is z over y, regardless of zeta, is 1. So if you guarantee that the sensor, the seismic unit you are using is in this range, I said omega is unknown, but you can expect omega. For example, let's say this is imbalance problem. Imbalance is due to a rotating eccentric mass. And the frequency of excitation is the speed of the rotation, or multiple of the speed of the rotation. Okay, so if you then you can expect that the frequency will be frequency ratio will be omega over omega n. Omega you will take it as the speed in radian per second, or twice the speed, or 3 times the speed, or 4 times the speed. Then you can get expectation range. Okay, and then if that ratio is high, then that sensor can be used here. The output of the sensor in this case is 1. Z over y is 1. Then it means, and we can measure z because this is part of the circuit inside the seismic unit. So z is measured and z over y is 1, then y equal to z with certain amount of error because this is not exactly equal to 1. Okay, unless it is exactly equal to 1, then the error is 0. And there are cases where z over y equal to 0, equal to 1 exactly, because you can see, for example, zeta equal to 0. This is zeta equal to 0. It is equal to 1 here at one point, which is not a feasible range. Okay, but at one point it is equal to 0. That's exactly equal to 1. But if you use it for the range that is omega over omega n is greater than 1, very much greater than 1, then you can use it for a bigger range. Okay, so the seismic, it is called seismometer in this case, that measures displacement. Okay, the seismometer is the transducer that measures displacement, because at this range you will have y is almost equal to z. Z is the one that we can measure from the sensor, from the seismic unit. Then we can say that with certain amount of percentage error. Okay, we will talk about the errors, how to calculate the error, because this is not exactly equal to Z. Okay, but if let's say that the error is plus minus 1, then that is a good value that you will get in the range of 1% plus minus, or we say 2%, or even less than 1%. It depends on the natural frequency of the system, okay, and the range of the frequencies. The other range, useful range, is when omega over omega n is very close to 0. There is an added graph here, not part of the equation, omega over omega n squared. This is added. Okay, I will change the color. So in this range, all curves are merging as omega over omega n squared, which means that z over y in this range is equal to omega over omega n squared, regardless of zeta. Okay, so when you multiply z times omega n squared and y times omega squared, what you get here? This value is the acceleration. Okay, we can measure z and multiply it by factor omega n squared, which is also we know. Then acceleration equal to acceleration. And this is what is called accelerometer, that measures accelerations directly. So in this range, you can use z over y. It is equal to omega over omega n squared, regardless of the value of zeta. But this is approximately equal to omega over omega n. Then you need to find the range at which you can, or you can find the error from the deviation of this. Okay, so those are the useful ranges that can be used to make measurements, either as a seismometer that measures displacement, or as an accelerometer that measures acceleration, but not frequency. In all this, you don't see the frequency. We don't measure frequency with this seismic unit. Okay, in order to measure the frequency, and there is direct way, but that will not be for all cases. So what you can use to measure the frequency is to measure y with time and use Fourier series, what we did in chapter 1. Okay, but I will not go to that part. That would be totally something different than what we are doing. Okay, we are focusing on amplitude here. If you want to find the frequency, you apply the Fourier series, and it's called harmonic analysis. I'm not doing harmonic analysis here in this course. Okay, so we will find ways to find either the displacement or to find the acceleration. So we have two types of sensors we can make, or transducers, out of this. Okay. Okay, let's see the notes on the graph. This graph is identical to that of mx over me, which is the impedance. The response are function of two parameters only, omega n and zeta, or omega over omega n and zeta. There are two types of instrument. Each one has different useful frequency range. Okay, so as you can see, the seismometer and the accelerometer. In order to be in the seismometer, let's say you want to measure frequencies in the range 10 Hertz, okay, or 20 Hertz. Then you can make a seismometer equal to, with a natural frequency equal to 1 Hertz, 2 Hertz, right? So that 20 over 2 is 10. and that will be useful in this range. Okay, if you want to measure acceleration, then you need to have a frequency of the seismometer, of the accelerometer to be very high. So suppose here you are measuring frequencies in, let's say, 1000 kilohertz, 1000 hertz, or 2000 hertz, or 1 kilohertz. Then you need an initial frequency of very high, 10,000 kilohertz. So that 1000 over 10,000 is 0.0, maybe 1, right? So that you have a small number, and the frequency range is very small. So if for accelerometer, you will have the seismic unit with very high natural frequency. Okay, and also in order to make this frequency very high, it means you need a small mass and high stiffness. And this makes the accelerometer to be small in size. The seismometer on the other side is you need a small natural frequency or low natural frequency. Then you can make the mass high and the frequency low, and this makes the size big. So the seismometer is bulky. The accelerometer is, you can say, there are accelerometers which are called tiny, very small, and the one we use in our phones are accelerometers. So they are not affecting the size and the weight of the phone that much. Okay. Seismometer, they are their mass is large or high. So when you put it on a small machine, it will affect its vibration characteristics. So you cannot use it everywhere. You can use it only on surfaces which are heavy, like the turbines, big machines, so that it will not affect its dynamic characteristics. Accelerometers can be used almost everywhere on any casing of machines. Okay, but there are uses of seismometers and there are uses for accelerometer. Okay, in the seismometer, it is used to measure displacement. Okay, also can be used to measure velocity. Okay, let's talk about one by one. Seismometer, which is the instrument with low natural frequency, if n is very small. The natural frequency of the instrument is so low so that omega over omega n is large, because you are dividing by small number. Omega n is small, you are dividing by small number, becomes large number, omega over omega n. Okay, provided that omega is not in the same range of omega n. Omega is 10 times, 20 times of omega n. Okay, so in this range, we have z over y equal to 1, almost, regardless of the value of zeta. The mass is, in this case, when you have z over y is almost equal to 1, the mass of the seismometer become stationary, because x equal to 0. In order to have z over y equal to 1, it means that, and z is equal to x minus y, so it means x is 0 in this case. So you have only the casing is moving, and inside the mass is not moving. Okay, only the casing. Okay, one of the disadvantages of the seismometer is that its size is large. That's the main disadvantage of the seismometer. Okay, otherwise it can measure directly the displacement. And if you put a magnet mass inside instead of mass, usual mass, this is magnet mass, and you put coil, and then you will have the velocity is directly proportional with the flux. So you can use this to measure velocity. Seismometer can be used to measure velocity, and it's called velometer or velocity pickup. Okay, it measures velocity. The output voltage is proportional to velocity, and the output, the voltage, voltage becomes directly proportional with velocity. The initial frequency of seismometers lies between 1 and 5 hertz. Okay, the useful range is from 10 to 2000 hertz. So that when you divide, let's say, by the maximum, you will have the range is 2 to 40 or 400 hertz frequency ratio. So it is very high frequency if you make the nature frequency low. Here is an example. It shows the seismometer, a high sensitivity seismometer. The nature frequency is 1 hertz, and the mass travel is plus minus 1 millimeter. Its diameter is 15 centimeter, and its weight is 11 pound. Okay, 11 pound, which is almost 5.5 kilogram. Okay, so you cannot use this on small machines. Okay, and the equation of the Z over Y, if you look at the same graph here, this is to be used for the seismometer. So for example, if zeta equal to 0, and this question will be, what is the useful range of using this seismometer with a percentage error equal to 1, for example? So you can take an example of a seismometer with zeta equal to 0. Okay, the question will be find the useful range the useful frequency range with maximum error equal to 1%. How do we measure the error here? We are saying that if Z over Y equal to 1, the error is equal to what? 0. So 1%, it means the deviation from the line Z over Y equal to 1. Okay, that is the error. So Z over Y is called the error factor, not the error. And the error itself, let's say E, equal to 1 minus Z over Y. So it is the deviation, the deviation from one, either plus above 1 or below 1. The difference between this value and of Z over Y and 1 is called the error. So let me just give you from the graph there. Okay, this is Z over Y equal to 1 here. Okay, let's take it is moving from 0 and become asymptotic, right, to 1. Okay, the error is 0 here. If the error is 1%, it means you need either this part and measure from 1 is 1%, or here. Okay, this is also 1%. So it is either a plus or minus the deviation from 1. So if error is required to be maximum 1%, we don't have equation for the error. We have the equation for the error factor. So we need to calculate the error factor. Okay, the error factor for 1%. For 1% error is either which is Z over 1 equal to 1.01, this is 1%, the deviation, or 0.99. But in both cases, for each case, if I use 1.01, I will get a different range than when I use 0.99. Okay, so when you use 0.99, the range will start from this point. If we use 1.01, the error will start from this point. The frequency range will start from this point. So which one I should use? For zeta equal to 0, I will use the second one. Why? Because you can see this is higher than 1%, near resonance. Okay, so it depends on zeta. For zeta equal to 0, I will use 1.01. But for other cases, for other values of zeta, you have to check the peak value. Okay, this is for zeta equal to 0. It is obvious that the error factor equal to 1.01. For other values of zeta, for seismometer with zeta not equal to 0, okay, we have to check the peak value. Of the error factor. Okay, let's say zeta equal to 0. Let's say 0.6 as an example. And maximum error required is 1%. Or 2%, whatever, just an example. No? Then the error factor will be either 1.01 or 0.99. So I need to choose one of them. So first of all, you check the error factor at peak. Okay, how do we find the error factor at peak? It is at the maximum, at the maximum of Z over Y. And this is obtained from D error factor by differentiating by dr. R is omega over omega n equal to 0. And this will give you the frequency at which the error factor is equal to maximum. Okay, I already added this in the formula sheet. The error, we call it R peak equal to 1 over square root of 1 minus 2 zeta squared. Okay, I will make sure this is correct. In the formula, it is in the formula sheet. Okay, this is the formula sheet, 2 pages, as I told you. The second page is for chapter 3 and chapter 4 as well. Okay, so here is the error factors in instruments. And the first one is for seismometer. The second one is for the accelerometer. So this is the omega over omega n peak. You see the equation is equal to 1 over square root of 1 minus 2 zeta squared. This means this is the frequency at which the error factor is maximum. Okay, so when you go back to the, for zeta not equal to 0, okay, here is 1. We'll go with the maximum, then go back, right? We have to check the peak value here. This is R peak, which is equal to 1 over square root of 1 minus 2 zeta squared. Okay, and depend on the value of zeta. And then the error factor here is called error factor peak by substituting in the equation of Z over Y with R peak. And we check this value with the given error. Okay, so let me find. Oh, time is over, right? Oh, over 10 already, 10 minutes more. Okay, so I'll stop here. يلا يعني سويت نفس